Welcome to this installment of Availability Workbench Helpful Hints. In our last installment, we discussed optimizing inspection or condition monitoring intervals. In this video, we will examine how optimized maintenance strategies impact spare parts holdings. Today, we're going to talk about the factors to consider when optimizing spares and the interaction between spares holdings and maintenance strategies. Lastly, I will go through an example in Availability Workbench using the file from the previous session about optimizing condition monitoring intervals. Multiple factors must be considered when purchasing and keeping a spare part. Chief among these are the cost of ownership and the business impact of not owning the spare. The cost of ownership includes the original purchase price plus the cost of holding the spare. Holding costs can vary from 10% to 30% of the purchase price when you consider factors such as interest on borrowed money, the annual cost to operate and maintain the warehouse, and inventory taxes in those places where inventory is taxed. You will need to work with your accounting department to determine those annual costs. The lead time for the spare and its impact on the downtime costs of the failure will usually heavily impact the business. The storage requirements may play a role, especially in cases where weight and size limitations impact the system, such as on ships and oil platforms. As we saw in our last installment, the majority of equipment likely benefits from condition monitoring, so we will focus on those items. Let's take a look at the model. We'll start by looking at the spares information for this spare motor we have. At the general, we can capture the price of this thing in order to buy it. At level 1, we can capture how many we're keeping in stock. At this point, we're only going to keep 0 in stock. And we can capture the storage cost rate per unit. So that's based on the purchase price of $5,000 and the carrying charges. In this case, we're going to have 20% per year. And then we divide that by the number of hours in a year to get the storage cost per hour. So $1,000 divided by 8760, we come up with 11 cents per hour for storage cost per unit. Typically, we'll have 0 in here for the logistic delay time because we would usually be able to get those parts while the item is being torn out of the system and have those parts over there by the time we want to put them in. Not always, but most of the time. Or if you do have a system where you've got a logistic delay from your spare storage area to your equipment, you'd want to put that in there as a logistic delay. Now we'll go look at level 2 properties. Now, level 2 is a little bit different. Again, we're going to put a 0 in there for now so that we're starting out with nothing for spares. And we're going to run the model with no maintenance turned on and nothing in spare parts so that we can start doing some comparisons here in a little bit. So we get a little discount on our storage rate because we're sharing this storage with somebody else. That may not always be the case. You may be, if you're on an oil platform or remotely located, that storage facility may be shore instead of on the platform. So you have a logistic delay to get from the shore to the platform, and this would cover that logistic delay, and it might be anywhere up to 3 days. It just depends. Does it have to come by boat? Does it have to come by air? How much does it cost me to move this part to where I need it at level 1? In this case, we say the delay is 1 day or 24 hours, and we get some discount because we're saying we're storing it with a sister plant and we're sharing the storage cost, so it only costs us 6 cents per hour for storage. The thing to be careful of on level 3 is mainly this logistic delay time. The logistic delay time shown on level 3 is the time it takes to get the part from level 3, which typically would be the vendor, to level 2. So if it's not going to come to level 2, you would want to subtract the level 2 logistical delay from that delay from the vendor, because the delay from the vendor would get you all the way to where you're going to use the part. So the delay from the vendor plus the level 2 delay would be the total delay that you would see for the part. And we're going to say that it's the delay distribution is fixed. That means it will always be the same. Not necessarily correct, but probably pretty close. Then over here for optimization, we want to make sure that we put in the minimum number we would want to keep in spares and the maximum number we're willing to keep. We may not be able to keep more than 3. So if that's the case, in here we put 0 and 3. And in level 2, we may be only able to keep 3, so we put a 0 and 3 in there. And what will happen in the program is it will optimize storage at both of those locations based on the overall cost for both locations summed together. So now let's go run the model and we'll see what the impact of no maintenance. Let's make sure the maintenance is turned off over here. So we've got our PM turned off. Whoops, our inspection is still turned on. So let's go turn it off. We'll disable that task, give it an OK. So now this is a totally reactive organization. We're going to have the failure. We'll get the part from the vendor. The vendor will deliver the part and we'll do the repair. So we'll run the model and we can see that we've got total cost in the range of 2.8 times 10 to the 8th for the consequence cost, around $20,000 for the cost of the part, for a total of roughly 2.9 times 10 to the 8th, or $290 million in cost, and that's generally related to the fact that it takes 2 weeks to get the part from level 3. So now let's go optimize the spares without doing anything with the maintenance. So we'll go to our spare cost optimization and see if we can figure out what the value of having the correct number of spares is. Now this shows a level 1 optimization, optimum level, but you can see there's an asterisk there, and that means that optimization is out of date. So let's run the optimization. And it is determined level optimization of 1 for level 1 and 2 for level 2. So let's accept that recommendation and see what the impact has been on overall cost. And we can see a decline in overall cost from the 10 to 8th to 10 to the 6th. So we've gone from hundreds of millions to millions. So having those spare parts is very, very valuable, especially if you have a long lead time. Now I know it's a no-brainer to keep something that takes you 2 months, but this will help people see the value of having done that if you need to be justifying those spare parts. So now let's go look at our maintenance strategy and see what the impact of that is. So we'll go into the maintenance strategy, and all we're going to do is enable the inspection, because when the inspection is done and finds the potential failure, what will happen is that the PM that we have in the system will be completed. So it's a PM replacement. So let's run the model, and we can see that even with the spares that we have, we've reduced our costs down into the 10 to the 5th area, right? So now let's go look and optimize our spares based on the fact that we're doing maintenance. So we'll go to our spare cost optimization window. We'll select the spare. We'll run that again. And now we can see that it's running several scenarios down here. It's going through each spare and looking at it based on having done that new maintenance strategy. And we can see that the level 1 optimum remained at 1, but the level 2 optimum has reduced from 2 to 1. So let's select that, close out, and we'll run the model again and see that we're still in the 670,000 range for cost. But one of the things that we see here is that we've got some planned consequence cost. Now the reason we have that is because the PM task shows that the system is non-operational when you're doing this PM, having found it based on an inspection. So let's go look at that PM and see if we can make a little change here. We'll go to the Advanced tab, and we'll say that instead of being non-operational, it's operational. And the reason we'll say that is because typically we won't suffer specific downtime for doing that PM. It'll be put in with other work that we plan on doing, either as opportunity maintenance, or it will be put in with other work we're going to do on a scheduled maintenance. So we can say that it's not really not operational, it's just that we're going to do the work. So let's see what impact that has on the system. And we can see now that our total costs have gone down to tens of thousands, not hundreds of thousands. We're suffering very little cost for corrective work. Our corrective consequence cost is only around $15,000, whereas before it was several million, several hundred million when we were running to failure. So in this case, you can see the value of having the spares. You can see the value of optimizing the maintenance that you're doing and making sure that you're getting the most value out of the maintenance strategy that you're using today. Today, we looked at the factors to consider when stocking maintenance spares and the relationship between maintenance strategies and spare holdings. We saw the importance of having the right level of spare parts to minimize overall cost and the impact that optimizing a maintenance strategy has on the number of spares your organization needs. Thank you for watching this video. Please contact Isograph for more information by visiting their website or calling Brett Peterson at 801-610-0045.